Good morning, everyone. Welcome back to already the last lecture of this week. Next week we have 4 more lectures to go. This morning I posted the grades for assignment 1. Did everyone see the grades? So the request is, if you have any issues with your grade, right, you don't agree, you think you're treated unfairly, please use the next lab session to discuss it with your TA. Right, so if you convince your TA that you deserve a high grade, right, I instruct the TAs to, if they agree with you, just to up your grade in Canvas. There's no discussion. If they agree with you, there's no problem. If you agree with the TA, right, after discussing that your grade is correct, fine as well. If there is a discussion, right, that you cannot resolve it like in 5 to 10 minutes, please don't argue any longer with your TA. Just report the complaint on the mailing list to me, and I will try to solve it. And so use the lab sessions to discuss this. But if you cannot resolve any disagreements, please report to the mailing list, and I will try to solve it for you. So that's about disagreements. In the grade, you will also see the feedback in the rubric, right, about what you did correctly and what you did not correctly. Please spend some time trying to understand this, because in assignment 4 you will be given the opportunity to implement any improvements that you can still make on assignment 1 and assignment 2. Right? So the more you understand the feedback, the more you learn from this assignment, but also the more chance you have to improve on this in assignment 4. So before we start the lecture, are there still any remaining questions about assignment 1? Okay. So on Monday I devoted 2 lectures on JavaScript, right, which is assignment 2. And I'm now going to switch to the HTTP server side of web technology, which will be assignment 3. Now, my experience over the last years has learned that for some of you, the switch from assignment 2 to assignment 3 is really easy, right? And for some of you, it's conceptually a hard switch to make. So I want to give that some special attention. Let's get some chocolate. So, I've talked about these concepts of the client versus the server, right? So these are 2 different roles on the web, and you have basically 2 different machines connected by the internet talking to each other. So if you have the client on one side and the server on the other side, right? This is your mobile phone or your laptop, the machine that you use to access the internet, and your browser that's running on this machine sends a request to the server. For example, if you want to get access to the free home page, right? There's a server somewhere on the internet that hosts the domain Vigo.nl, right? There's a server program working here that serves your request and sends you back the HTML, the CSS, the JavaScript, whatever. Right? So that's the communication going on. So the browser is here, the client. And this is server. Now you get the HTML and the CSS and the JavaScript from the server. Still, the server doesn't do anything with it. All the interpretation of the code happens here. So that's why we call HTML and CSS and JavaScript, we all call it client-side technologies. Because all the word processing of the HTML code, of the CSS rules, of the JavaScript code, it all happens on the client side. The server code, the code that you're going to write for assignment 3 next week, runs here on a different machine. Right? So the Node.js code that you will write here will run on this machine. So this is the server side. It's really, really different world conceptually from what happens here. Right? So everything that happens here you test by loading it into your client. That's why it's called client-side technology. Here you need to start a server, and then when you start a server, nothing happens, right? Just the server starts, and the server will be waiting for requests to come in. So you need to test it by sending requests. For example, by a browser, but we will see in the assignments that there are other ways to test it. Right, so in principle, what happens here is really different from what happens here, not only because it runs on a different machine, but also because it really serves a different role. Right? So here, the role is to show you things, show you the HTML, render the CSS, run the JavaScript, and here the role is just to serve these content to requests coming in. Are there any questions about that? Okay, so what is new this year is that we will implement the assignment-free server using the Node.js platform. It is now has become lately really popular. So the chance that you will ever use this in practice later in your academic career or in your initial career is much larger than a little bit toy academic Python environment that we used in previous years. So I think this is much more real world than the previous assignment in previous years. It's also much better covered by the Zybook. I think it's really a good move. But the consequence is that the programming language here is JavaScript again. So it means that we will use JavaScript both on the client and on the server. Now, JavaScript was really developed originally to run on the client, right? So in a lot of literature, JavaScript is also called a client-side technology, but it has evolved, right? And people discovered that it had also properties that made it really suitable for running it on the server. And for example, a framework like Node.js is popular for many reasons, but one of the important reasons is that the JavaScript engines nowadays are really good at processing multiple requests at the same time. Right? So if you have a popular server that gets thousands of requests per second, there are many frameworks that cannot handle it, but JavaScript and Node.js are doing this very well. So we will be using JavaScript in the assignment 3, also on the server. But I want you to make conceptually this distinction between clients and servers. Now, so the one thing that might lead to confusion is this JavaScript on the server side. Another thing that is causing confusion is the use of the internet in the assignments, right? Because basically we don't make any use of the internet. And I will shortly give some attention to that by going back to the initial internet protocols that were in the shortly, very briefly described in the Zybook section 1, right? But very shortly. And if you use the telephone metaphor that people sometimes use, that sometimes helps to explain these internet protocols. So the protocol is the set of definitions that we use to communicate with each other. Right? So the nice thing about the internet is that you can communicate with different machines from different brands, and that requires some standardization. We need to have some agreement on how we set up these communications between different machines from different brands in different countries, etc. There are different sets of agreements, and we call these protocols. And the Internet Protocol itself already started in the late 60s and 70s, right? So this is much old, part of it is much older than the Internet, than the World Wide Web. And the basic protocol is the Internet Protocol, or IP for short. And one way the protocol works is by assigning a number, like a telephone number, to every device that's connected on the internet. And that That number is the IP address. It's a 32-bit number. You typically write it in this dot notation, right? So there are 4 numbers from 0 to 255 max, separated by dots, and that's your address. And like in the telephone system, right? If 2 mobile phones have the same number, you get conflicts. So you need some organization that makes sense that tries to make sure that all these numbers are unique around the world, and that's the Internet Assigned Numbers Authority, IANA. So that's a very important organization, and who governs this organization, right? This has been lately a topic of discussion, because it used to be a completely US-controlled organization, and there's discussion about this. And on the internet, you send packets of information from the source, a machine with an IP address, to a destination, also a machine with an IP address. And how that works is more in the telephone, maybe more like the postal network than the telephone network. Right? So you wrap your information in the postal system in an envelope, right? You put your brief, your letter in an envelope, and you put the address and the source of the source and the destination address on your envelope. And that's the same with the internet protocol. So you have a header that lists the source IP number and the destination IP number, and you put the thing on the network, and every step of the way the machines processing your requests look at the destination and forward it in the hope that it will get closer to your destination and finally will arrive. So it looks much more like a postal system than a telephone network. Now, if the machine that processes your requests knows the computer with the destination address, but it recognizes the IP number, I think, oh, I know where that computer is, and I can send the packets directly to it. It will do that, and if not, it will send it to a special computer called gateway. Right, so it looks like this. If you have the source on the top left, and you want to have a package sent to a computer that's outside network 1, the source will not know what to do with it. It will send it to the gateway. Suppose that the gateway recognizes this is not something from network 2 or network 1, so it will also not know what to do with it. It will have its own gateway to defer the package to. And it will go on and on until you come to a point that the gateway knows where the destination is and delivers it to the destination. Right, so this, in this way, the source doesn't need to know where the destination is. So you can scale this up big time, right? So this is also why the internet scales so well. The source doesn't need to know where the destination exactly is. It just needs to trust the gateway that if it sends the message to that, the packet to that finally it will arrive, hopefully. But there's no guarantee that this will succeed, right? So normally everything works well, and your packets get delivered, but there's no guarantee in the internet protocol that this will finally happen. So it's a best effort, right? Everybody does his best, but if it doesn't work, you can't complain. And also another limitation is that the communication is one way, right? There's a source that puts on the destination, and it's like the postal address, the postal system. In principle, this communication is one way. And if you want to send the package back, you just do it twice, right? So there's no notion of connection. But there are a lot of situations where these limitations are a problem. So in practice, IP is typically used in combination with another protocol, TCP, that's built on top of IP, and that guarantees that the package will be delivered, because it will just send the package again if it doesn't get the confirmation that the package was successfully delivered. And that sets up a communication, two-way communication connection. So this already feels, when you have a TCP connection on top of IP, it feels much more like your telephone analogy. So how does it look like? Right, it's really, really low level. So on the left you have the source machine, on the right you have the server, destination machine in this case, and the source wants to set up a connection using TCP. So there's a special TCP package format to ask the server, please can I talk to you? And if the destination agrees, it will send a message back. That's okay, can I talk to you? And then the source will send another third message to confirm, to acknowledge that everything is okay, and then we have a connection. And then it will send the first packet with the real information. The destination will acknowledge that it has received it. Hopefully it will do that. In the second example, it will send a packet, but the destination somehow fails to acknowledge that. Maybe it never got it, and the source just assumed it was so. But after some time, there's a timeout, and the source thinks, oh, maybe something went wrong. I will resend the packet, right? And then the destination does receive it. If not, they'll resend it again, etc., etc. Right? So this is the low-level stuff that happens on the TCP level. Now, with current technology, right, every normal operating system in daily use supports this. Right? So if you buy a Windows machine, Windows will know how to do this. If you buy a Linux machine, same, a Mac, the same, all your phones, this is all built already in the operating system. There's no need for the browser to do this. The browser can just request the operating system that is running on, please give me a TCP connection with this machine, this IP address. Okay. Now, if you have a server machine running here, right, it might respond to HTTP requests, but it might also, the same machine, physical machine, might also respond to email messages, and to make sure that all these different applications can run on the same machine. There's also this notion of a port, which is a simple number that you put in every header of every packet, and if you assign special numbers to special applications, this helps to run several applications on the same machine. So some of these ports have standard meanings, and some of these ports are just free for you to use for whatever application you want. Right? And 25 example is used for email. We saw port 80 used for HTTP. So if your application sends a message and you don't see the port, it's because the application will know to fill in this port. So if you don't add a port number to your URL in your web browser, the web browser will just fill in port 80 for you without you knowing, and then all the communication goes well. Now, except for TCP, there's another protocol that's also built on top of IP and also provides a port concept, which is UDP. And it's different from TCP, that you have no connection concept and no transmission guarantee, right? So it's much more bare bones IP. But it also makes it more lightweight and faster. Right? So, and there are several types of applications where being fast is more important than being reliable and make sure that all these packets arrive and are resent if not. And so, can anyone of you give me one example of an internet application where you don't want packets to be resent?
Voice chat?
Voice, yeah, why not?
Because you want to keep hearing the person on the other side. It doesn't matter if there's a bit of noise.
Yeah, so if there's a tiny part of your voice in the telephone conference missing, right, that is less annoying than if you're going to wait for 2 seconds for that tiny bit to be resent, and there will be a gap of 2 seconds, right? So voice is a typical example of an application that you can better implement on top of UDP than TCP. For example, live video is often also implemented on UDP. Because also they are right, the image freezing completely to wait for one tiny fragment to be reset is more irritating and more annoying than just continue and have a slight flicker in one part of the stream. But most of the applications that we on the database use TCP and IP. I want to come back to make the whole analogy complete to this domain name service, right? So this is also a typical exam question to explain what the domain name service does. And it maps between the domain names that we use on databases and the IP addresses, right? So IP addresses are hard to remember for humans. And DNS itself is also built on top of the internet, of course, right? And it's often implemented on top of UDP for efficiency reasons. And these domain names, of course, also need to be unique, right? Otherwise, we have a problem. In this case, it's not IANA, but the Internet Corporation for Assigned Names and Numbers, ICANN, that does this. And it works also in a hierarchy. So the domain part at the right, top right, it's called the top level domain, and typically ends on .com and .org or .nl, for example, for country codes. And these all have their own domain name service. So if your application wants to look up www.example.org and it doesn't know the IP address and doesn't know where to send the DNS request to, it will have a built-in IP address for the .org domain name server, so for all these top-level things. And .org is supposed to know what the DNS is for example.org, and the DNS for example.org is supposed to know what the domain IP address is for www.example.org. Right, so here in a hierarchical fashion, you can also make this scalable, so that not everyone needs to have a complete phone book of all the domain names in the world. But you can distribute the lists to the different places in the hierarchy. But that means that the domain name server that you use for your machine, right? So in this case, if you're using Adiro, the DNS is either provided by the VU or by the internet provider from the VU, needs to know all the top-level domains, right? And the corresponding IP addresses of the domain name services that it can request the domain from. So that means the more of these top-level domains there are, the more work it is to make sure that every DNS in the world knows these top-level domains. So people are a bit restrictive in adding new top-level domains. It's easier to add these second-level or third-level domains because nothing needs to change, right? But if you add a new top-level domain, and sometimes this happens, it's a lot of work because all the DNS services in the world need to install this. Okay. So, right, the analogy is never 100%, but more or less. IP, more or less, the telephone network. TCP is like really calling somebody up, wait until the other party answers, and have a conversation two-way, and then agree to hang up at the end. UDP is more asynchronous. You just send a message and you hope it arrives somewhere, maybe on an answering machine, but you never have one-to-one synchronous contact. And DNS is more like looking up a phone number, a telephone number based on the name. So this is the stuff, the internet as it was before the World Wide Web, right? And everything that the World Wide Web added was on top of this and makes use of this. If this wasn't there already, it would never have been, I think, the success that it was as it was now in the 90s. So We have many high-level protocols built on top of TCP/IP and UDP and DNS, right? And email and FTP were already there before the web, and the web with the HTTP protocol was just one of the many. And in the beginning, it didn't seem that it would become so important compared to the other two. And it's only later that it became dominating a lot of the traffic on the internet. So again, if you have a source and a destination, in the web, the source is typically the client, right, and the server, the destination is the server. That does not necessarily need to be the case. They can also have an equal role. And then you, for example, call it a peer-to-peer network, where all the different machines have a similar role. So they can also, the destination can sometimes take the initiative to contact the machine that previously took the initiative. But that's not the case on the web. On the web, we also always have this strict client-server roles, where it's always the browser that takes the initiative, and the server just waits and responds to requests. And that's actually the case for all these protocols, right? All of the client-server architecture. All these protocols also need to be managed and arranged, right? And there need to be organizations governing this. So most of these internet protocols are governed by the Internet Engineering Task Force, IETF. And the people that participated from the 70s in these task force, they had a really dislike of international standards, right? So because in those days international standards were governed by the United Nations in an organization called ISO, and was super democratic, also super bureaucratic. Took years and years and years to standardize things, and of course on the internet things need to be fast and quick, and people started to organize themselves in this IETF organization, which was much more rough consensus, right? So no documents with 1,500 pages of how to make things work, just a rough, this is how it needs to be, this is the example in the code and it works, and let's go with it. So that's still the spirit in IETF today. And also they didn't like this word standard, so you see the term request for comments. Right? It sounds really informal. Right? This is just a document with a request to comment on it. In practice, it is a standard. Right? So formally, TCP IP is defined in these documents called requests for comments, but they serve as a standard. And they often collaborate with other organizations like IANA and ICA and W3C. Now, when Tim Berners-Lee invented the web, he wanted IETF to standardize HTML, and IETF said, well, HTML is not internet protocol, so we're not going to do it, go to ISO. And also Tim Berners-Lee didn't want to go to ISO, so he organized himself in W3C and make sure that all these standards, content standards like HTML and CSS were standardized by W3C. But HTTP is still an internet protocol, right? So HTTP is still, even if it's very core to the web, it's still done by the IETF. So the HTTP protocol, it's a very basic request response protocol using this client server computing model, right? So it's always, the request is always sent from the client to the server, and the response is always from the server to the client. both the client and the server in this context are software programs running on these machines, right? So this is the client is your browser, and the server is the Apache web server program or Microsoft Internet server program, whatever. A piece of software running here. In other contexts, people can use the device, the hardware. Refer to the client meaning the hardware, or refer to the server meaning the hardware. But in this context, we refer to the server, to the software. And typically, the server provides content, right? HTML files, CSS files, images, JavaScript files, etc., etc. And these are all called resources. So to be as generic as possible, whatever the thing is that the server sends back, it's a resource, and a resource has one particular thing. It has a URI as its address. So everything that has a URI is called a resource, and you can ask as a web browser to the server, please give me this resource. And the response contains the resource, but also some status information to see if everything worked well. And that's also a requirement for Assignment 3. We will come back to that. Now, like I said, these URLs are really important. Also because in this internet network, how to address things have been a long discussion. And Tim Berners-Lee decided just to skip that whole discussion and just use the concept of a file name, as you find on your computer, right? Everybody knows how file names work. Every program on your computer knows how file names work on your computer. And just make something that works on the internet that looks as much as possible to a file name. And the URLs are basically that, right? So if you look at the different portions of the URL, what is here in red, right? /A, B, C, right? Is what really looks like a file name on the Mac and on Linux. On Windows it will be \A, \B, \C, but it will be familiar to many people, but also to many programs and programmers. If you look at the other parts, this is the host name, right? So this is the domain name system. That was already there, so everybody knew that as well already. So if you're on the internet, and you want to address a file, the file name itself is not sufficient. You also need to specify on which computer, right? So this is done by using the DNS. We have this port number, right, which is the port that you know from TCP. Was also already there, and the agreement was that if you just use port 80, you can. It's optional. You don't need to put it there, so nobody does. But it is there in principle, and together, right? It's called the authority. That's the specification of the program that is the authority or that is responsible for giving you the response. And then we have the path, right, which is basically the file name in the pre-internet era. Then we have a potential query, which comes after the question mark, which is sent to we use to send parameters and extra information to the server. And then we have a so-called fragment identifier. So this is not as common, but still used a lot. Do people know what you typically put after the hash? What the role of that is? So people, yeah?
The part of the page you want to go to?
It's typically part of the page identifier, for example, right? The ID element or the name element in your HTML, identifying what part of the page you want to go to. And this is a bit special because it's not sent to the server. So it's stripped off by the browser before it sends the request. So the rest is used to make the connection. But this is more for the browser itself, for the client to scroll, for example, to paragraph 5 in your document. So the browser uses the information in the authority part to set up a TCP connection, right? And that's easy because you can just ask your operating system to do that for you as a browser server. You put in the request URI the path to request the specific resource, so what page do you want? And again, if you don't put anything there, there's the sensible default, which is just slash, which means I want the home page. And the fragment identifier is stripped off and typically used to scroll in the browser to a specific place. So conceptually, right, there is this abstract thing as a resource. So suppose we are, in this case, requesting a weather report page. And that weather report page will have a URL, right, which is, in this case, weatherexample.com. And it has some representation. In this case, some HTML. But both things are not the same, right? So this is not the weather report, it's the URI of the weather report. And this is also not the weather report, it's the HTML representation of the weather report. And in common daily speak, right, you can often make sense of people not being very specific about this, right? So it doesn't matter. But in some cases, and especially if you're doing web architecture or you're designing your own services, right, making distinction of things is really important. And one thing is that, in principle, the same resource can have multiple representations. Right? So sometimes maybe you don't want the weather report in HTML, but you want the weather report using JSON data, so it's easier to process. And you can have an index.html version that does the HTML version and an index.json that does the JSON version. Then you have two resources with two URIs with two multiple representations. But you can also map both on the same URI and you say that the JSON is a different representation of the same resource. Right? And then you need to have other ways to ask if you want the HTML or the JSON. And both things are possible. And in the last scenario, it's really important that you distinguish between representations and resources. So a resource, in principle, can be anything, right? Typically, we think of resources as things that are on the web. But if I invent a URI for myself, right, then I can be a resource. How to identify and give URIs to things that are not on the web, that are not documents on the web, is still a debate. So, for example, for books, right, we have ISBN numbers that are unique, and ISBN numbers also have URI syntax, right? So books themselves can be on the web, be a resource, right? And then with the book, I don't mean the physical representation in an e-book, but just the concept of the book, right? So Hamlet of Shakespeare, right, in a specific edition has an ISBN, so is a resource, independent of whether that text is available on the internet. Yes, I will skip the secondary resource part. So once the web became successful, right, you saw that more and more non-web applications use this idea of identifying things with URIs. So suddenly, email addresses, right? You can now write mail to column and then your email address, and it's also a valid URI. So more and more applications use this notion of using a URI, and you get this network effects because now also browsers understand email addresses, right? Because it's just a URI. So if you click on a mail to URI, your browser will know, okay, I need to open the mail client on your phone or on your laptop. So a good practice is to identify anything where you're even if you don't have a direct web application in mind. And once something has a URI, you can create a link to it in any context. So in the old days, in the Web 1.0, that means you can have a hyperlink in the text to your, for example, to your mail address, which is the example I just mentioned. That in the text, you have a mail to my email address, and if somebody clicks, it opens your mail client. But you can have also links in other contexts, right? So you can have hypertext links to things in the JSON file, in the data, or in your spreadsheet. And your spreadsheet will understand that it is a link to whatever. See a question there or not? No, okay. Like I said, the same URI, right, can have multiple representations. And this is called content negotiation, and the HTTP protocol allows you to specify, I like to have this, this resource in this specific format. So for example, every time your browser requests for a home page, it will tell the server that it likes to have it in text HTML as a mount type, right? That's of course a bit of redundant information, but in principle it can also request other types of content. Now, for example, for audio and video and image formats, it's much more important that both sides understand which formats they do understand, right? So for video, there are so many protocols that as a server, you cannot implement and provide for all, but also as a client, you cannot implement and provide for all. So it's handy if the browser says, okay, I can understand these video formats, and then the server can see, okay, which of these can I serve to the client. Before the break, just the basic things. Like I said, we started by using the URI, this authority part, to set up a TCP connection. So once I have this, I can start sending messages from the client to the server, and I do that using the HTTP protocol. So these are the rules on how to create these requests, and they are really simple. And for each function, for each purpose, there is a request method. And all the methods have short names, like get and post and head. We have seen get and post already in assignment 1. When you do this form, for example, we use post, and every time you load your web page, it does a get. And these messages are just sent in plain text. We will come back to that later. Oh, sorry, we come back to that now. So suppose we have a URI typed in our browser example.org/test HTML. What the request message looks like, sent over TCP, is literally the text GET space /test HTML space HTTP/11 for the version. Right. So what do you see here? The browser will have used this part to set up a connection on port 80, TCP IP connection with the server, right? And then once there's a connection, it says I want a resource using the get method. This is the name of the resource. This is the version of HTTP. This allows you to do different things in the future for different versions of HTTP. And then again, it sends the web server the host name, right? Which is the name of the server itself. So the first thing, right, makes complete sense. This is what you want, and this is the second line this is how you are called as a server. So why does the client need to tell the server what his name is? It sounds a bit Like we shake hands, you tell me your name, I say what I want, and then I say, again tell you what your own name is. That sounds weird. And to give you a hint, in HTTP 1.0, the second line was missing. And in HTTP 1.1, this second line is obligatory. So it went from missing and not even possible to obligatory and necessary. So anyway, why do you tell the server its name?
There could be multiple websites with different names on
There can be multiple websites on the same server with different names, right? Because the DNS right, allows you to have multiple domain names mapped to the same IP address. You can even have multiple IP addresses for the same hardware. So you can have multiple host names on the same machine. So what's the typical case where you would want that? So if we go to, for example, if we go to Vuno.nl, right, will that machine also serve Uva.nl? Personally, I think not. But if I go to my personal website, which happens to be ossenburger.com, is that server also completely devoted to my little private email address, or are there 100 different servers running there? Right? So I have my own personal web service hosted by my internet provider, right? And my internet provider does this for thousands and thousands of clients. And of course, they don't have a separate machine for every client, so they run the same server for different websites. And every website has its own domain name, so you need to tell the server, okay, this is a request for this domain. So this switch from HTTP 1.0 to 1.1 really became necessary when internet service providers started to host websites for multiple clients. Okay, I want to keep it at this. Let's reconvene at 12, and then we finish the rest of the lecture.